CompSustNet with support from the National Science Foundation and Cornell University. We are happy to offer this opportunity to those interested in computing and sustainability across the globe. You can find the schedule for virtual seminars at the URL at the center of the slide that's currently up, as well as recordings from past seminars. The next virtual seminar will be Friday, December 15th with Professor Nicole Sintoff. My name is Doug Fisher, and I'm the Director for Outreach, Education, Diversity, and Synthesis of CompSustNet. During the webinar, you can ask questions through chat or the Q&A facility on Zoom, which will be relayed to the speaker as time allows. If you would like, find the chat window now and write hello to everybody. It is our pleasure today to have Professor Michela Milano. Professor Milano is a full professor of intelligent systems at the University of Bologna. Her research activity covers methodologies and techniques for design and development of decision support systems in several areas. She's a member of the executive committee of the Italian Association for Artificial Intelligence and is a counselor of the Association for the Advancement of Artificial Intelligence. She's also a recent winner of a Google Award for the integration of deep learning techniques in combinatorial models. So, Michela, it's a pleasure to have you today. We're going to let you take it from here.
Good. Okay, so welcome everybody, and thank you for inviting me to give this seminar. I'm working at the University of Bologna in the Department of Computer Science and Engineering, and my background basically is on decision support systems and optimization systems. And I've worked in the integration of techniques from artificial intelligence, namely constraint programming, constraint satisfaction problems, and operations research to create hybrid optimization systems. And more recently, in the last 5 or 6 years, we have worked in the integration of machine learning techniques into optimization problems, combinatorial optimization problem. This is very important. So this is indeed the topic of the talk, the seminar. And so let me start with some motivating examples. So first motivating example is the following. Suppose that you have traffic light placement problems. So you are in a city and you want to add and remove traffic lights over a whole city. And basically traffic lights can be connected like in green waves, and every operation has a cost. There is a budget, of course, and there are also probably other constraints, combinatorial constraints that are not considered here. And we want to improve traffic figures. What are these traffic figures? Like, for example, waiting times at traffic lights, or we want to, for example, improve the travel time or the queue length. And we want to solve this problem. So which is the toughest obstacle that we have to consider? We have to understand which is the effect of traffic light placement into traffic levels. And this is really hard to design because expert design declarative models do not have any analytical form. We have to model human behavior, and we have an underlying complex system, which is the traffic index. So what we have to do is to understand if we call the traffic light placement, so our decisions as decidables and the traffic levels as observables, we want to understand the impact of decidables on observables and cast this impact into an optimization model. So let's take a second example. I mean, if you want to interrupt me, I mean, just do it at any time. So as a second example, suppose that you are in a region and you want to devise some policies for PV adoption. So you are an energy policy maker that should take into account energy policies, and you want to foster photovoltaic adoptions in your region. What you can do is you can devise some incentives. So you want to achieve a target PV adoption in your region, and you want to decide which incentives to give. Every incentive has a cost, so you want to allocate some budget on each incentive. Like incentives can be investment grants, feed-in tariffs, rotation funds, guarantee funds. I mean, whatever incentive you have to design, you have to allocate some money on it, But you have to understand the toughest obstacle of this problem is to understand the effect that these incentives have on PV adoption. And this is a very tough problem. We have to work with many governments working on energy policies, and they do not have any idea on which is the impact of the incentives that they provide on the real adoption of photovoltaic plants, for example. Why that? Because we have to model the human behavior, we have to model the social dynamics, and this is really tough. So again, if we call our incentives as decidables and the PV adoption level as observables, again, we want to understand the impact of decidables on observable and cast this into an optimization model. Third example, which is the one that I will use as a working example along the seminar. So we want to basically dispatch workload on an architecture, on a computing architecture in a thermal aware mode. So we have targeted heterogeneous platforms, then we have a workload that we should run on the platform, and we want to decide basically how to allocate these tasks of the workload on the resources of the architecture. Every task has a thermal dynamic, and there is in general a thermal controller. And we have, for example, load balancing constraint and other deadlines and many other side constraints. But we have some thermal limits, and this is a very tough problem. And I will dig a little bit into the details of this problem. So why it is important? This is important because the cooling cost in computing is increasing. Just think that basically almost 40% of the total energy demands of data centers are due to cooling infrastructure. So this is, of course, this does not have a favorable environmental footprint. It brings emission, and it is getting really worse. Why it is getting worse? Because this is a trend of the top 500 supercomputers in terms of floating point operations per second. And in 2020, we are expecting to reach exascale computing. And you know what? So the expected energy for exascale computing is around 170 megawatt, which is the 30% of the energy budget of a today nuclear reactor. So that's really a huge amount of energy that we have to deal with, while the feasible exascale power budget is below the 20 megawatts. So we have really to take into account any technique to reduce the power consumption. And of course, the power consumption of the cooling system does matter a lot. So we have started from embedded systems. So, and then we can scale up to high performance computing system, to data centers. So we are we have considered in our case study an Intel single chip cloud computing. It is a platform. It was an experimental platform by Intel, and this is the father of the Xeon Phi platform that is now used in many accelerators. So this is indeed was an experimental platform. So it has a 48 cores, a network on chip, and 4 memory controllers, right? So why we have to take into account the thermal part? Overheating is really a bad thing. Why that? Because we risk to damage the chip, we have reduced performance and reduced lifetime. And traditionally, we use thermal controllers that simply slow down the chip when the temperature goes high. And this leads to poor performances. So we want to obtain proactive techniques where we need a thermal model, and we have to somehow dispatch the workload being aware of the thermal part. So this is really an interesting problem. Why that? Because the behavior of a multi-core system, so the temperature, the thermal behavior depends on many, many factors. The first one is the room temperature. The second is the workload on each core, the chip fabric, the position of cores and the heat sinks, heat transfer between cores, and also the fact that there is a controller on the chip that slows down the speed of the chip when the temperature gets too high. So indeed, here we have a connection between the workload that we put on the platform and the temperature, because we have a very accurate thermal simulators. And these thermal simulators indeed mimic the thermal dynamic of this architecture. And basically they model through differential equations, they model the thermal behavior of the platform. But we cannot simply put these differential equation in a combinatorial model and hope to have a solution in a short time. So what we rely on are expert design models that in general are oversimplified, and they do not really capture with the proper accuracy the thermal dynamic of this platform. So going back to our example, what we have, which is the toughest obstacle, is to understand the effect of workload allocation on the thermal dynamics, right? Okay, so basically we have optimization, we have simulators for that, but they are not manageable by combinatorial optimization techniques. Okay, so this is our problem. Okay, so we have decidables that are workload allocations, and observables that are the temperatures of the course. And we want to understand the impact of decidables on observables and cast this into an optimization model. So the main research questions that we are doing, so just a second that I have to switch on the, okay, so the power to my computer. So the research question that we have to answer is, how can we learn the relation between decidables and observables? Well, let's take again our previous example. So the traffic light placement. Okay, what do we have at our disposal? So what we can count on? We can count on data, first of all. So we have a lot of traffic data. These traffic data are, for example, origin-destination matrices. We have flows on the different roads that are extracted by sensors. We have a lot of sensors in our roads, and they provide us traffic data. On the basis of this data, we can devise traffic microsimulators. What is a microsimulator of traffic? It is a simulator that basically has different agents that are vehicles, and these vehicles basically have a dynamic that interacts with the infrastructure and with other cars, other vehicles, with pedestrians and so on. So they end up to be pretty, pretty accurate models of the traffic. So what we can do with these simulators? We can sample the observation space by running the simulation with different inputs of traffic light placement and produce a training set. Indeed, let me spend just one word on that. So this is a traditional what-if analysis. Simulators indeed are used by decision makers to make a what-if analysis. And the what-if analysis is, I try to give to the simulator my decision and I see what happens, okay? So indeed, this what-if analysis is used by decision makers, but suppose that we have in this case, as we have in this case, a very complex environment where we have many different combinations of decisions. So if you think about the number of intersections that we have in a city, so kind of 200, 300 intersections, and you have to understand which is the proper combination of traffic lights, then the number of possible combinations is huge, okay? So you cannot really sample all of them. So you have to decide which sample to take. And this is something that I will say, I mean, this is a very important problem. I will say something in the end of this talk. And we produce a training set. So we produce a training set where that is sampled here. So we have a placement as an input, and basically the traffic light figures that we want to measure as an output, and we can produce this nice training set. So we can do with this training set, we can basically learn an approximate function of the simulator. And this is very similar to a surrogate model. So we want to learn a function that links the placement of traffic light to traffic levels. And this is a first example. Second, this is an important part. We want to cast this learned relation into a combinatorial problem. And we want that this relation works into a combinatorial problem as a constraint, as an objective function, and it works actively to reduce the search space. This is the gist. Okay, second example, our policies for PV adoption. What do we have available for learning the relation between decidables and observables? We have data, historical data on PV plants installed. We have previous incentives that have been given by previous regional policies. And possibly we can have also questionnaires, surveys, and interviews. Why do I need all this stuff? Well, this is really a very intricate problem because economic factors are not the only factor that is affecting PV adoption. Let me just show you an example. These on the left part of the slide, we have the incentives that have been given as feed-in tariffs in Italy per kilowatt hour. And this is, on the left side, this is the adoption, so the PV plants installed. I mean, as you can see, there is not really a direct relation between incentives and PV adoption. Why that? Because there are not only economic factors that drive this adoption. There are social factors, that are social dynamics. There are individual factors that are taken into account, trust in government. There are, so the imitation of the neighbors that have the PV plan installed. So there are many aspects that can be taken into account. But we want to extract from these simulators, social simulators, for example, or from data. We want to take, we want to create a training set that links the budget to provide incentives to the PV adoption, okay? And again, we want to run a machine learning model on top of it, like, for example, a regression tree, and then we want to cast this machine learning model into a combinatorial optimization model, okay? So this is the important part, casting the machine learning model into the combinatorial model. Third example, which is the one that I will dig a little bit more into the detail, is our thermal aware workload dispatching. What do we have at disposal? I mean, what are the data that we have for doing that? In general, in computing systems, we have access to the monitoring data of the real system. So we can really monitor what's going on when I put some workload on the platform, okay? So I can run different workload dispatching on the platform and then observe which is the temperature, which is the power, and I can create a training set also here. And what we have done is that basically on a multi-core platform, we have devised a neural network, a small one, on each core. And in the neural network, as an input, I have, for example, the room temperature, and also I have aggregated features, and this is very important, of the workload that I dispatch on each core, okay? So the ACPI is the average clock per instruction that I put on a core. This is my decision, and I want to observe the temperature and want to predict the temperature after a delta T, okay? So this is very important that we are extracting some features from my decision, the dispatching decision, and then want to forecast something for the observables. And then cast again this learned model into a combinatorial model, okay? Okay, so these are the motivating example. And what do these motivating example have in common? First, we have a very strong combinatorial structure. And this is maybe the most important part that differentiates our approach from, for example, black box optimization. Part of the problem cannot be easily described through a declarative model, or the declarative model do exist, but it is not manageable from a combinatorial optimization perspective. And three, we have access to problem data that are either historical data or simulated data, or data from the real system that we can monitor, we can see, we can observe, we can collect to create a training set. So in principle, we have a combinatorial optimization problem solver on the left that provides a solution to a black box solution evaluator. And this black box solution evaluator basically is the one that provides the link between decidables and observables. And the black box solution evaluation provides an evaluation back to the combinatorial optimization component. This is very similar to Banner's decomposition indeed. But of course, the black box solution evaluation is not simply a problem decomposition, it's just a black box function, okay? This black box function can be very expensive to be evaluated, very expensive. We have, for example, the scatter search plus system simulator in a system called OptQuest by Manuel Laguna. That is a system proposed in 2011. So the scatter search provides a solution. The system simulator that is very expensive is the solution evaluator that provides back the evaluation to the scatter search. So this is somehow a generate and test procedure. And the OptQuest improves this procedure because since the system simulator is very expensive, then I can insert into the scatter search a predictor, so a machine learning model, that somehow evaluates the simulator outcome. It predicts the simulator outcomes and basically avoids to evaluate those solutions that are trivially unpromising, so of low quality, for example. So basically, I will evaluate only those solutions that provide a promising outcome from the predictor, okay? So the predictor somehow enable a selection of solutions, but still, this is a generate and test process. I generate a solution, I evaluate it afterward. So what if the black box tool is a machine learning model? So, and not a simulator. So I can somehow decide that the simulator is too heavy, computationally heavy. So I want to approximate it through a machine learning model. So there are a number of papers on this topic. And these papers are on surrogate models. And surrogate models, among other techniques, are also relying on machine learning techniques. So, for example, the first paper here is relying on artificial neural network. The second paper by Kodasainis Del Miller, which is a more recent paper, relies on a function that is composed by base function fitted on the data that then are somehow improved through an iterative process. But still, the machine learning model can be very expensive to train, but after the training, so the training can be done offline, but after the training, then the machine learning model can be very efficient to use, okay? So, I mean, just asking a trained neural network, which is the outcome given an input, the output given an input is very fast. But this still is a generate and test mechanism. What does empirical model learning do? Is to really encapsulate the machine learning model into the optimization component. But the machine learning model is not just a module that provides me a yes or no answer. It provides me, or an evaluation function. It provides me an operational semantics that helps me reducing the search space. And this is crucial in empirical model learning. So this is not limited to objective function. We can learn constraints, we can learn coefficients, we can learn any relation between decide-ables, that are our decision variables, and observables. Okay, so I have cited here a paper that has been published earlier this year, and that describes the overall process, and that this is basically the base of this talk. Okay, so take again the first example on a traffic light placement, okay? So I have really overly simplified the models here. I mean, just to give an idea, just to give a hint, okay? The models are much more accurate and more complex. I want just to give you an idea, a very intuitive idea of what we have done. So the combinatorial component on its own is the fact that we have some variables that decide that are 1 if we want to place a traffic light at a given intersection J, 0 otherwise, okay? Very simple, linear model, integer linear model. Then we have a budget, placing traffic light as a cost, and then we have a cost constraint that is limited on the budget. Then each variable can be 0, 1, and then we can have many other constraints like incompatibility between intersection, or intersection that require neighboring intersection to be inserted, and so on. So what we can do is that we want to really understand the impact on traffic of our decision. So we can have a neural network per road learning the impact on traffic using basically, so as input, our decisions. So our decisions are the input, or somehow features extracted from our decisions are an input, and the output is the impact on traffic, okay? So what we want to do is to cast this neural network on in a component. We call it a constraint. It is an empirical model learned that links the impact on traffic with our decision variables. And this is a constraint that propagates, that reduces the search space, that actively works in our combinatorial model, okay? And then, for example, we want to maximize the positive impact on the traffic, subject to all the constraints that we have in the combinatorial component. Second example, policies for PV adoption. Here I don't have 0, 1 variables. I have integer variables that somehow decide the budget allocated on every incentives. And I have a constraint limiting the budget, okay, this one, plus many other constraints. For example, in a given region, I cannot provide more than this an incentive for a given renewable energy source. Why that? Because I don't know, there is not enough sun, there is not enough wind. I mean, these are really other constraints that I really don't take into account here. Then we can have, for example, a regression tree that relates the budget allocated on incentives, our decision, to an observable, the PV adoption. So I can squeeze this regression tree into an empirical model learning component, which should be, for example, a constraint that relates my decision, the X, so the budget allocated on the incentives, on the PV adoption, and then acts as a constraint in the combinatorial model. Then I have all the other constraints that I have described above. And also, of course, a constraint on the fact that I want a specific target PV photovoltaic adoption in my region. Why that? Because I have planned for that. Third model, and this is the one I will go a little bit into the details. So we have a neural network per core. We have a variable xij that is 1 if task I is allocated on core j. And so these are my decisions. Where do so which resources are used for each task? And then, of course, I have constraints that say that one task should run on only 1 core. And also I can have a load balancing constraint. I'm really overly simplifying. I mean, the model is much more complex, but anyway, I'm overly simplifying for the sake of clarity. So I have a combinatorial component, I have a machine learning model, and a method for squeezing, for encapsulating this machine learning model into my combinatorial model. So I want to minimize the maximum temperature achieved in each core, because is the parameter that I want to keep low, okay? And then I have all the other component combinatorial constraints, and the constraint linking the workload dispatching to the temperature, plus other constraints that I'm really not interested in now. So the thing is that we want to do is to squeeze, to cast an the machine learning model into an optimization component. So, and this is the question that I will try to answer now. How to cast a machine learning model into a combinatorial optimization component. Okay, the second question of empirical model learning, beside embedding a machine learning model into a combinatorial component, is how do we provide operational semantics to these models? So why do I want to provide operational semantics? So I want that these components, the empirical model that I've learned, do work in the search space by removing part of the search space. I want that the search space is explored in an intelligent way, in a smart way. I want to remove, sub trees. I want to remove branches as soon as possible. So I want really that this empirical model works in the combinatorial optimization search. I don't want it to be just black box stuff that is there and evaluates. It should be actively involved in the solution process. So during this talk, I will try to explain you how to embed neural networks and decision trees, mainly in constraint programming, which is because constraint programming is really suitable for hosting these methods. But I will say something also on mixed integer nonlinear programming, integer linear programming, SAT modulo theory, okay? And in the paper that I have cited in the AI journal earlier this year, there are many examples involving also these techniques. But I also, for the limited time that I have for the talk, I cannot cover really everything, but I will try to give you some intuitive ideas. Okay, so the first is how to cut an artificial neural network in a combinatorial optimization component. Okay, so what is a combinatorial, an artificial neural network? We have input nodes, output nodes, and one or more hidden nodes. Now in deep networks, we have many, many hidden nodes. But the deep networks are a tricky guy to take into account. I mean, they are really tricky. I will spend a few words at the end. Okay, so basically, every neuron has a number of inputs and a number of inputs that are weighted by weights that are learned during the training phase, okay? These inputs are, so we have a weighted sum of the input in the neuron activity A, plus a bias, and the output of each neuron is an activation function that is monotonic and non-decreasing, that is applied to the activation, to the activity of the neuron to produce an output, okay? Good, so this is a constraint. So that means input with output. And a whole neural network is indeed a declarative model, a declarative nonlinear model. So, for example, if we have a MinLP solver, we can simply, as simple as that, casting the equations of the neural network into the MinLP model. This is very simple. We have to provide variables for the input, variable for the outputs, and simply put the equations in the model. We have to be careful about problems related to numerical precision and accuracy, but still, I mean, this is very, very simple. But if we have a hard combinatorial structure and we have a constraint programming model, what can we do? Well, this is very, very nice. So we can devise a constraint, a global constraint, that model a single neuron, okay? It takes input variable, x, output variable, y. It has been, so these are weights that are the result of the machine learning model that has been done offline to understand the relation between decidables and observables, and a bias, okay? So this activation function can really propagate backward and forward. So when I have a machine learning model and I want to forecast the temperature of a core given its workload and the workload on the neighboring cores and the room temperature and whatever input you want to give, machine learning model function in forward. So you give an input and they provide you an output. I want that the machine learning model works also backward. So if I put some constraint on the output, I want that the input is pruned. So the input is, that decision that do not lead to feasible output are pruned. And this is really the important part. So how can I filter a constraint that has an activation function and how can I filter the single neuron constraint? So if I update the maximum in the input, so on the activation function, I can of course update the range, the domain of the output. But vice versa, if I update the output, I can propagate back to the input by removing those decisions that lead me to an infeasible output. And this is very important. So I can filtering from Y to A and from A to Y, given that I and Y are two decision variables of my problem. So we can combine many neurons constraints in artificial neural network global constraint. So we can have really a constraint that has an artificial neural network inside, which is very powerful. So let me see how, let me show you how it works at search time, okay? So we have our multi-core, so here for the sake of simplicity, I have just reduced it to a 4-core architecture, but we can have as many as we want. Here we have the tasks that we have to allocate. So then when we take a decision, we can compute some features that are extracted from this decision. For example, if I allocate some workload on a core, then I can extract some features from this workload allocation. And these features, for example, are the average clock per instruction that I have allocated on the core, okay? Plus I provide the room temperature. On each core, I have a neural network that estimates the temperature that I will achieve on the core after a given delta t, okay? And I have 4 in this case of them. I can have many of them. So when I allocate something on a core, then the neural network shows me that there are some temperature that increases after a while, and it provides me a hint on the temperature that I achieve on the core, okay? So I have a feature computation starting from my decision that go into the input of this neural network, and then the neuron constraint provide me the temperature after, so the observable. So the allocation is decidable, I decide this, and basically the temperature of the cores is an observable. And in the network, I put the workload on the core, the workload on neighboring cores, because they are affecting the core, right? And but the important thing that I want to do is that I want to propagate forward, so from the decision to the temperature, and I want to propagate backward, and this is the key. So if, for example, I have a threshold on the temperature, so I don't want my cores going more than 70 degrees Celsius, then what is important is that the neuron constraints enable me to remove infeasible assignments that I would have instead otherwise tried. So the neuron constraint really creates a link between decidables and observables. So the decidables are the workload dispatching, the observable is the temperature, and if I have a constraint on the temperature, then I can remove infeasible assignment. And this is a way of exploiting machine learning model that has, as far as my knowledge is concerned, I've never seen. So the backward use of machine learning model to remove infeasible decisions. So the CP model for this problem, again, I'm overly simplifying, but this is somehow more accurate than what I've explained you a few minutes ago. We have n tasks with the clock per instruction values that somehow give so to give us an idea on how, the task is, so how power eager is the task, so, and how the temperature is related to the task somehow. Each task is assumed to run indefinitely. We have 48 cores, we have a room temperature, and basically we have decision variables explaining where to put each task on my cores. And we have load balancing constraints saying that for in each core I should have roughly the same numbers of tasks per core to have a load balancing heuristic. And then we can also have equivalent allocation variables that are the Xij I was talking about a few minutes ago, that are one if the task J is allocated on core I. And then here is our empirical model learned. So I compute an average CPI per core, and this is a feature extraction. So when I decide an allocation, so a value for Xij, I extract some feature of this allocation, and these features are fed into a constraint, okay? And then here, this neural network constraint is my empirical model. I have input variables, so the average CPI on the core that I'm considering, and the average CPIs on the neighboring components, plus many other functions many other features that I can extract, plus the room temperature. And this neural network component provides me a hint on the core temperature of the core J. And I have many neural networks, one per core in my model. And these constraints propagate backward and forward. And this is really important because this constraint really enables me to propagate and to reduce the search space. The objective function that I want to minimize is the one that I have told you, and is the maximum temperature over the core. So this work has been described in a AAAI 2012 paper, and the important thing is that here, by observing the model, so by training the neural networks, I'm also observing the behavior of the controller that is running on my architecture. So I can really observe the system in its running situation. And this is very important because I can really have an idea of what is going on the platform. So these are some results. These are reported in the AI journal paper, and basically on the left hand we have the heat generated, so the red there, the hottest. This is the heat generated on the cores of a very sophisticated mixed integer linear programming model using an expert design model, and the expert design model has been devised by experts working in a data center that are really knowing how things are going on, on these platforms. Okay, so you will see these red spots. These are hot spots in my architecture that are really not good. Why that? Because I need to cool them down, and possibly the temperature controller may slow down the performances of the cores. On the right-hand side of the slide, so this part here, this is the heat generated on cores on the empirical model learned through neural networks. And as you will see, here we don't have much red hot spots. So the room is much more homogeneous. We have much cooler zones, and indeed the load has been balanced, but not just by load balancing constraint, but by the fact that the model was aware of the thermal component that was much more accurate of an empirical model, of an expert design model, of which, by the way, we don't know the accuracy. So an expert in general provides us hints on his model, but we really don't have any hint on the accuracy of the model. Okay, so this was an example for the neural network casted into an optimization component. Now we will talk a little bit about decision trees. So we have decision trees are another very famous way of learning, classification problems. We have random forests that are indeed used instead of decision trees in general, but still, decision trees are very popular, okay? And we have tried to understand how to cast a decision tree into an optimization model, a constraint programming model, or an optimization model. So we have many encodings. So here I will explain two. So what is a decision tree? A decision tree is, as an input, training set is a tuple of attribute values pair, and output we have a class. And attributes can be either numeric or symbolic. On numeric attributes, we split by deciding a threshold value and splitting, okay, values less than or equal than 20, greater than 20, while symbolic attribute can be splitted by taking into account each value per branch, okay? The leaves of decision trees are classes that I want to classify, okay? So when I have a new example, I want to classify it, and I simply go down into the decision tree and I will end up in a class. Very simple, as simple as that. So how do we embed decision trees into constraint programming? First, I need to have a decision variable for each attribute, for each feature. So the feature extraction part is really important. So they can be either A and B can be numeric, C is symbolic, and the B or is somehow, binary. It depends on the problem that we have to take into account, and the class can be symbolic. So we can define a constraint again. That is a decision tree constraint. So it's a machine learning model that encapsulates the decision tree that I have learned offline, observing the system, observing the data, the training set that I have. And now when the system is trained, I can cast this into an optimization model. And this is the tricky part. So the first thing that we can observe is that the path is an implication, okay? For example, in this case, we can say that if A is greater than 20 and C is 0 and B is greater than 20, then the class Y is 1, okay? So this is simply an implication. Very, very simple. So a class can be described as a set of implications. So the tree defines all the paths. So Y is equal to 1 in 3 cases. Either A is greater than 20, C equal to 0 and B greater than 20, or A is greater than 20 and C is 1, or A is less than or equal than 20, C is less than or equal, B is less than or equal than 10, C is 1, and A is also greater than 10. So we can really create all these paths as an implication, okay? So we can simply encapsulate all these implications into a constraint programming model, into a SAT modulo theory model, and we can really use them as part of our model. Can we do better? Yes, we can do better. So why that? Sorry, let me go back 1 second. This is very interesting because it is a polynomial size encoding. It has a polynomial time propagation, but we do not achieve generalized R consistency. So we have room for improving the propagation, okay? So these implications do have an effect on our tree, but they can have a larger effect, a stronger effect. So we can do better, in fact, because in constraint programming, for example, do exist constraints that are called table constraints. So the table constraint basically links set of assignment with a value, okay? And so they basically indeed model feasible tuples of assignment. So as a tuple of assignment, we have the value of the attributes and the class, okay? So these are already provided into CP Solver. So if we cast a decision tree into a table constraint, then the game is over, right? So this is very, very simple. We have, so continuous attributes, of course, here are a little bit tricky. Why that? Because in the table constraint, we have discrete values. So we have to discretize the continuous attributes, but this is simple. Why that? Because in the decision tree, we have threshold values on which to partition the decision tree, the continuous attribute. And so this is very, very simple, because we can use this discretization point for discretizing our continuous attributes, okay? So we have compared many different encodings, and the table constraint provides us generalized R consistency. So we cannot do more in terms of propagation as using the table constraint. Of course, there is always a trade-off between propagation and efficiency. So we have really to be careful in understanding these trade-off between efficiency and propagation, okay? So this is, for example, a graph where we have compared local search with this CP with what is that? So this is the CP with the encoding used based on table constraint, and the blue one is the encoding with the implication. Okay, so even the simplest encoding, so the implication one, indeed performs better than local search, but it performs a little bit worse in terms of solution quality than the GAC. Why that? Because generalizer consistency is the maximum form of propagation that we can achieve in constraint programming, and using large neighborhood search, this red curve can close unpromising neighborhood very quickly. So we have used also other encodings, MDDs, for example, compressed tuples, negation normal forms, decomposition approaches, and we are basically writing now a technical report that is comparing all these kind of encodings. Also, we have identified how to cast variants of decision trees, like regression trees, multi-output trees, random forest, into constraint programming approaches and SAT modulo theory, and so on. And basically, we are comparing different methods and how do they prune, how do they actively work on the search space in combinatorial optimization methods. Okay, so some concluding remarks on what I have said. So basically, empirical model learning really enables combinatorial optimization over complex real-world system where we do not have models that are either have an analytical form or can be computed and evaluated in a short time. So this has a very, very close relation with black box optimization, but we have a combinatorial structure that is really, really tough, and this is very important, okay? Of course, this is not the only solution, and it does not need to be about CP, but indeed CP is really well suited for empirical model learning because we can compose different empirical models that are learned beforehand on data, and we can really exploit them at runtime. So it's very easy to embed a machine learning model in constraint programming, provided that we are able to provide an operational semantic that actively works in my combinatorial model. And of course, constraint programming is very flexible, modular. We can add and remove side constraint very easily. And the empirical model is just a constraint, just another constraint. So we have some issues that we need to take into account if we have to make it work. So the first issue is you can always embed a machine learning model, so an evaluator in a local search or meta-heuristic, right? So you can embed it into genetic programming, particle swarm optimization, all the meta-heuristic that you want to think about. But can CP work better? Yes, it works better. Why that? If we have a combinatorial structure that enables the propagation. If we don't have a combinatorial structure, then I mean, these methods, local search and meta-heuristic, can work really, really better. So if we need inference method for machine learning method, then really, CP works really well. And inference methods are propagation methods that enable us to reduce the search space, and they should be effective, provide me tight bounds, and should be efficient. So they should be computed at each node of the search space, so they should be efficient. So the second issue, which is very much related to the first, is should I try to use machine learning models that are very complex but very accurate, but they may end up with slow and weak propagation, or simple machine learning models that are less accurate for the model that I'm learning, but they provide an effective propagation? This is really an unsolved question, so we are trying with different problems to try to understand. But this is really a trade-off between accuracy and optimization quality, okay? So we have to find design rules, we have to characterize it. And you know what, we are trying to use a deep network today, in these days, to encapsulate deep networks into constraints. This is a topic of a Google Faculty Award that we have now. And the nice part is that deep learning networks are really, really very accurate, but embedding them into a constraint is really tough, because in the same way as gradient vanish in the different layers, this happens also to propagation. So it's very difficult to find how can I say, effective techniques to propagate a neural network backward and forward, a deep network backward and forward. A third issue concerns the training set. So I have really said very quickly, we sample the simulation space and we somehow extract the relation between decibels and observable. But this is really a tough point. Why that? Because historical data can be somehow predicted. So a machine learning model provides a prediction of my input data, but then you know what? It happens that the final solution can end up to be here and the true value can be here. So there may be a very large error. So we can really have to choose the representative observation. And here, this is a work in progress. We can borrow concepts from black box optimization and the construction of surrogate models that really work very carefully with this detail and iterate many times to try to measure the difference between the true value and the predicted value, and adjust the model to basically meet the value and increase the accuracy, like by adaptive sampling. This is a Cyanidis work on surrogate model that is really working on. Also, fourth point, can we take into, machine learning model at the end of the day provide confidence level, right? So can we use this on the test set, but also on the training set? Can we use this when optimizing? And the answer may be, here I have some strange, animation, sorry for that. So, and of course, we can use these confidence level when optimizing, okay? So we know that the result of the machine learning model is not exact, but can vary between, minus and plus 5%. So we can take this into account for creating, for example, robust optimizers. But also we can take into account uncertain input and employ machine learning model, empirical model learning in stochastic optimization. So these are all issues that are current subject of current research. But the toughest issue of all is that optimization researcher like clean declarative model and machine learning researcher seldom use decisions as input. So we really need to work together and create a community that works on these two topics together. But I know that you guys working on computational sustainability are used to work in very multidisciplinary environments, and this is, something that you are used to do. So we really should work together and bring together researchers in constraint programming, machine learning, operation research, management science, and to bring optimization methods really to a real world system. And this is requires an effort from everybody. So this is all I wanted to say. I hope that the connection was fine and you could hear everything. And now I'm ready to answer to your question if you have some.
Well, thank you so much, Michela.
Thank you.
Are there any questions? We have time for one or two. So, Michela, this reminded me somewhat of work in the, I don't know, it's probably the 1980s on learning search control rules for, optimizing search. And I would, in addition to the communities you mentioned, I wonder whether there is current research on learning search control in the combinatorial search community. And they might be a community to bring and to involve too.
Absolutely. So there are some papers that are using machine learning models, for example, in a large neighborhood search for understanding. So large neighborhood search works as follows. So you have a solution, you fix some part of the solution, and then you search exhaustively the rest. And for choosing the neighborhood, choosing which variable to fix, so there are machine learning models indeed. And there is a very interesting paper by Yves Deville, Pascal Van Enterich, I think, on this subject. And also I think that there is much room for improvement in this area, because search is indeed a part of the optimization strategy that can learn. Of course, there is all the research part on no good learning that is very active, but this is something, different. This is something related to the model. But I'm really sure that in the search control community, there is plenty of room of using machine learning model for reducing search space, or even trying interesting direction of the search. So even tree search and meta heuristic, both of them. This is really a very promising direction, Doug, definitely.
Okay, very good. Jen Wen has a question. Do you want to ask that yourself, or you want me to ask it?
Either way is okay.
Okay, so go ahead.
Go ahead and ask it.
I have typed it in the chat.
No, but ask it. It's better if you ask.
Okay, so just a quick question, like about the scalability.
This is from Cornell, Michela. Hi.
Ciao. How are you? Happy to see you.
So I noticed there you've had a lot of applications in to embed ML into a combinatorial constraint. Just based on your empirical experience, what's the scalability of these methods?
Yes, this is a very good question. So the scalability, the scalability is a problem, in a combinatorial optimization, okay? So in general, so these scalability issues are still there. But basically, as soon as the learning part, once it is trained, so the learning component, once it is trained, then it's not really, does not bring into the optimization component much overhead. So of course, the training part might be very time consuming, because you have to deal with, observing a complex system and trying to devise, let me say, a surrogate model. This is a surrogate model, okay? But the thing is that we don't use surrogate model in a numerical optimization or as an evaluator, but we want to dig it into a combinatorial component. So the scalability issues are the same that we found in a combinatorial optimization, but yes, still are there. But it is not really worsened by the machine learning component. So the scalability is there for the combinatorial optimization model, not for the machine learning component. That might take very much time into the training part, not in the use of it. Because if it is trained, then the neural network is very fast. I don't know if I answered your question.
Okay, yeah. Thank you.
Mm-hmm.
We have one more question. Carla, do you have a question?
Yeah, I have a general comment, because I have
Go ahead. And then we've got a question on Zoom.
Okay, so go ahead with the question then.
Okay. Antonino asks, first says, very interesting talk, thank you. When you use the neural network in the inverse model, you can know that the allocation of 3 workloads, for example, to one core generates a too high temperature. So you need to remove some workload tasks from the core. But does the neural network model enable you to understand which task you have to remove? And also, with your approach, are you sure at the end you manage to allocate anyway all the workload tasks you need to?
So yes, I mean, basically in the example of the neural network, we have links between task allocation that are decision variables and features that I extract from the task allocation and from the feature to the temperature. Okay, so suppose, I mean, forget about the neural network. I mean, we have three parts that they are connected, they are linked. So when in the same fashion as global constraint work, as soon as you remove some bounds from the temperature, so in the temperature, then you somehow propagate back using the activation function and the way that you have learned, you can propagate back to the inputs, and then the inputs, okay, so sorry, CompSustNet requesting remote control, okay. Okay, so and then, yes, they are linked really to decision variables. So you can propagate back, and as soon as there is an assignment that would lead, so you don't try it, but it would lead to a temperature that is too high, you know that these 3 combinations cannot go together. So as soon as you do 2 of them, you can remove the 3rd. Or, I mean, in a global fashion, you can somehow avoid the 3 guys of being, so it's like when you have an all different, right? So in all different, you can decide beforehand that a given combination of assignment produces domains that cannot be allocated to different values. And so you will end up much before. So this is very similar. So you propagate back from temperature to allocations. I mean, there is an intermediate step of feature extraction. This is explained much better into the paper. Of course, I didn't have time, but you can really go back to your allocation variable. They are discrete values. This is an important part that I have to say. You have discrete values, and these discrete values have been used for training the network. And in this case, you can really go back to the variables and remove the values. And this is the important part of the method.
Great. So one last question, and then Carla will have a final comment. But this is again on the Zoom Q&A. If you want to look at that, just anonymous attendee asks, just a tangential thought question: could it be that genetic code, DNA, is an optimal fitting data structure for exploring a problem space akin to the EML class idea? The gene sequence is akin to a trained model.
Well, I don't know. This is a great idea, but I don't know. I mean, it could be. I mean, as soon as I mean, any method that could somehow extract relations. I mean, there is also a question between causal relations or simply relations. But anyway, so as soon as I can learn a relation between decidables and observables, and I can use this method for pruning, then I think that we can really encapsulate almost everything.
Okay, Carla?
Very good. Well, Michela.
Sorry, just a second. Sorry, there is someone. Just a second.
Somebody.
This is the quirkiness of virtual presentations.
This is the real world, the complex real world in action.
There's somebody at the door. Yep.
Yes.
So guys, sorry about that, but I am at home because my network at the university has some problems. So I am at home and my son is just ringing. So sorry about that. I try to. So sorry. Well, virtual seminar. Forgive me. Okay, so
Michela, we just number one, thank you so much. I know it's late there. It's like what, 7:30? So yes.
8:40.
8:40. Yes, yes. So thank you so much for accommodating. But I want to say, you know, this talk and your work really is emblematic of, you know, computational sustainability. You work on, you know, sustainability questions, but, you know, from a computer science point of view, you know, what I find exciting about these problems is really they force us to solve real world problems and address real world challenge. And you know, you bring together these embeddings with machine learning into CP and vice versa. You know, this is really pushing the frontiers of computer science, and it is truly exciting. Really, really awesome work. Thank you for your talk, and this is fantastic.
Thank you, Carla. Really, I mean, I appreciate it.
Okay, with that, we are going to sign off. Thank you so much, Michela. It was great.
Okay.
Great
Thank you to you for the invitation. It was really a pleasure.